Alright, now I'm going to take care of the second part of this problem. In the first part we did the t-test. Here in the second part we're going to do this proportion test. And we'll do it using both the classical method and the p-value method. So I guess we should go through and read the problem and figure out all the pertinent information. So it says, I suppose that the pressure of the playoffs increased. That'll be a key word right there. Jordan's win percentage. In all of his games, kind of a hint there that we're talking about the proportion, he won this percent of them. So that percent right there is our population proportion. We used to use the letter P to represent that, but we want to use the letter P for something else in hypothesis testing, so we're going to use P naught. Then we got this sample. There are 179 games in our sample, so that's N. And he won 119 of those games. That's not P hat, be careful. P hat is equal to that value divided by N. So 119 divided by 179. Figure that out if you wanted to. I don't know that it really matters, but sure, why not, as long as we're here. 119 divided by 179. In the playoffs, he won about 66.48%. Alrighty. So we can see that his playoff win percentage was higher than what he did in all games in the population. But the question is, can we conclude with 95% certainty? That's telling us that alpha is equal to 0.05. That it was being in the playoffs that increased this win percentage. Did this just happen by luck, or was this because it was the playoffs? All right. So the way we'll figure it out is we'll start by stating our null and alternative hypotheses. H0, H1. Over in our t-test, our null hypothesis compared mu and mu naught. Over here in our p-value test, it's going to compare p and p naught. P naught in this case being 0.65, 86. And similarly over here, we compared mu and mu naught, and then we figured out the symbol in the middle based on what the question asked. We're going to do that same thing here. We're going to compare p and 0.6586. However, the symbol in the middle, we'll have to go back and read the problem. It said increased here, so we want greater than. It says increased, so we're doing a right tail test. And so since it's right-tailed, our alternative hypothesis is that P is greater than this number. All right, now we can figure out the shape center spread. So it'll be similar to what we did in 8.2 when we were talking about sampling proportions. The shape is approximately normal because that is always our answer in this class. But maybe more importantly, the criteria that you'll have to cite is that N times P times 1 minus P is greater than or equal to 10. Problem, you don't know what P is. P is the population proportion, which we don't know. However, when you're going through the logic of these problems, you start by assuming the null hypothesis is true. You say P equals P naught. So we're going to use P naught all throughout this problem wherever P shows up. So if you want in your formula, you could write that. We can check that that's true. 179 times P naught was 0.65 something. It's going to be true by quite a bit. 6586 times 1 minus 0.6586. And if we multiply these things together, we're going to get a number way bigger than 10, 40. Maybe I could write it like this. N times P naught times 1 minus P naught is equal to 40.2, which is greater than or equal to 10. Good enough. Center should be given by P. However, we don't know P. We're assuming the null hypothesis is correct, so we're assuming that P equals P naught. So for the center, we're going to use P naught, which is 0.6586. Spread, sigma sub P hat. We used to have this formula that said that that was equal to the square root of P times 1 minus P divided by N. Again, we don't know P, but again, we're assuming P equals P naught, so we can change all these to P naught. And we could figure that out over here. We want the square root of 0.6586 times 1 minus 0.6586 divided by N, which was 179. Square root of that times that divided by that. You could close your last parentheses if you want to, doesn't matter. And you get this value, 0.0354. In other words, 3.54% is our spread. When we draw this picture that we're going to do down here, I can kind of ran out of room last time, so maybe I can be smarter about it this time, or maybe not. There's my approximately normal distribution. It's approximately normal because it says shape's approximately normal. The center is 0.6586, which has a z-score of 0. And I got to figure out my rejection region. The spread in this picture is this 3%. And the way I'm going to figure that out is I'm going to say, all right, I got a right-tailed test. So since alpha is equal to 0.05 here, I want a rejection region over here on the right-hand side with area 0.05. And I can figure out that area using my calculator. I can use inverse norm. The reason why is proportions follow a z distribution because we're only estimating one parameter. Use inverse norm, tell it the area below that point, which is 0.95. And then you don't have to put in comma 0, comma 1. But I'll do it to emphasize that we're getting a z-score here. Or you have this number memorized. However you do it, it's fine. You get this critical value of 1.645. So that lines up right there. So now what we got to do is find our test statistic, and if our test statistic is in the rejection region, we reject the null hypothesis. The way you do that is you hit stat and go over to tests, and this is a one prop z test. We're dealing with proportions, and we only have one proportion, so one prop z test. Hit enter, it'll ask you for p naught, which is 0.6586. It'll ask you for x. What x is the number of games he won in the sample. It's this number right here, this 119. Your calculator doesn't ask for p hat. It asks for the two pieces that make up p hat, this 119 and this 117, and then it calculates p hat for you. And our null hypothesis, or our alternative hypothesis, is that p was greater than p naught. So we have p is greater than p naught here. And if I go down to calculate, it'll give me my z, my test statistic, and my p-value. So what this is saying is I have a test statistic of only 0.175. It's way over here, 0.175. And that's the number that corresponded with my value of p hat, this 66.48%. So I got this 0.6648. Those were supposed to line up there. That's my test statistic. And note it is not in the rejection region. So maybe I'll write because my test statistic is not in the rejection region. And my test statistic in this case was the 0.175. So my test statistic, 0.175 is my test statistic. Because my test statistic of 0.175 is not in the rejection region, there is not sufficient evidence to reject the null hypothesis. I guess that's enough. There's not enough evidence to reject the null hypothesis. I'm not saying the null hypothesis is right. I'm just saying there's not enough evidence to prove that it's wrong. Okay, now we can do that one more time down here for the p-value method. The good news for the p-value method is it's a little bit quicker. We can just use this output here. We know that 0.6586 was in the middle, which had a z-score of 0. And then I have this test statistic of 0.1751. I just called it 0.175 up here, that's fine. That goes on this row because it's a z-score. And that test statistic right there has an area above it, above only because this is a one-tailed test, equal to my p-value, which is this 0.43. 0.431, I guess, if you want to round it off. So because my p-value which was 0.431 is greater than alpha, maybe dot dot dot, then what we do is we pick up here, there is not sufficient evidence, a lot of arrows, sorry. Because my p-value 0.431 is greater than alpha, there is not sufficient evidence to reject the null hypothesis. We have the pictures. Here's the classical picture, and here's the p-value picture, and there's my two conclusions over there. And that brings me to the end of this perfect problem, the end of the proportion hypothesis testing.